Swayam Prabha. Digital India. Educated India.
We were analyzing the flow in a microfluidic channel, a two-phase flow, and we looked at different aspects. Okay, but in order to do this analysis, we need to understand the fundamentals, and we want to be now shifting gears. Rather than talk of examples, we will talk of fundamentals, because once your fundamentals are clear, you will be in a position to apply all of that to analyze different problems. Okay. So, given any problem, any situation, you should be in a position to be able to formulate the problem, write down the governing equations, the boundary conditions, and then solve. So, all of this has to be done, but for that you need to be clear about the physics, so that you can write the governing equations. Then you need to write all the other things, that assumptions that you make, then you sit and worry about solving. Okay. So, let us with an idea of trying to understand fundamentals, we will talk about so, when you talk about fluid flow, there are basically two approaches which are used. Okay, and one is called the Eulerian approach and the other is called the Lagrangian approach. So, in the first approach, which I call the Eulerian approach, what we do is, supposing you are interested in making a measurement of maybe temperature or velocity or whatever it is, or pressure, you fix your attention at one fixed point in space. Okay, and then at that point you are making your measurement. What that means is, at that particular point, because of flow, the molecules which are going through that your probe are going to be different. Okay. So, you are measuring the velocity or temperature of not the same molecule, but of different molecules which are going past the point which you are focusing on. Okay. So, you are fixing the spatial position of the measurement, and the flow is happening. So, at every instant of time, the probe is measuring different molecules, whatever the property is, velocity or temperature, whatever it is. Okay. So, here we focus and fix our attention on a fixed point in space and measure, let us say, velocity there. So, this velocity is the velocity of different collection of molecules. Okay. So, this is what you are doing, and this is the typical thing you can do in fluid mechanics, right. I mean, if you have a reactor, you put the probe at a particular point and you make the measurement. What is the other approach? The other approach is to fix the probe on a particular molecule, okay, or a particular particle, and this particle is also going to move. the molecule is going to move because you have a fluid mechanics situation, fluid flow, okay. So now what you are doing is you are focusing your attention on a fixed molecule and this molecule moves around. So you are not fixing the space because the particle moves, okay. So that is called the Lagrangian approach. Here we fix our attention on a particular molecule. This moves around, okay, in the flow field. So, it will move in the flow field and therefore, your probe is measuring at different points in space. In the second approach, you are not focusing at a fixed point. The particle is here, the probe is here, let us say you have some infrared sensor or something, this guy is just moving around. So, at one particular time you are measuring the temperature here, another time you are measuring the temperature somewhere else, okay. So, that is the basic difference between these two approaches, okay. So, clearly the one what is feasible is the Eulerian approach, where we focus our attention at a particular point, okay, and then we make the measurements of velocity or temperature. That is the one which is practical. You put your thermocouple, you put your pitot tube, you put whatever it is at a particular point and then you measure the velocity at a point, okay. Then why are we even bothered about the second approach, Lagrangian approach? The Lagrangian approach we are interested in because most of the conservation laws are for closed systems, for a fixed molecule, for a fixed collection of molecules, okay. If you talk about laws of thermodynamics, that will be available for a closed system. So, basically the fundamental laws which exist like conservation of mass, momentum, energy, they are typically for closed systems or fixed collection of molecules. So, the fundamental laws are basically relevant in the Lagrangian sense, but what is of interest to us is the Eulerian method. So, what we want to do is we want to apply our fundamental laws, okay, and we also want to do Eulerian. So, what we want to do is we want to relate the Eulerian approach to the Lagrangian approach, okay. Eulerian approach is what is experimentally feasible. Lagrangian approach is where I can use, where I am talking about a closed system where I have all the fundamental laws. I am interested in applying fundamental laws like conservation of mass, momentum, okay. So, then I need to see how to take these fundamental laws to the Eulerian framework, okay. So, we need to understand how these two approaches are related to each other, okay. So, the fundamental laws of conservation of mass, etc., are valid for a fixed mass system or fixed molecules, okay. I mean, if you write Newton's law, force is mass times acceleration, that is for a particular molecule you are looking at, okay. You are looking at a molecule and say Newton's law, force is mass times acceleration. You are not applying it in a space. This is a body, how is the body accelerating? That is what you have done all along, okay. So, or for what is called closed systems, okay, and Hence, since the Eulerian approach is of interest to us, okay, we need to relate Eulerian and Lagrangian approaches. Okay. So, that is basically what we are trying to do now. Now, in order to make things a bit clear, what I will do is, we will focus on temperature. Say, supposing you have a particle here, okay, and there is flow, and this particle is moving. So, what have I drawn? This is the trajectory of the particle. So, at a particular time it is here, at a later time it is somewhere else. Okay. So, this line tells you what is the trajectory of the particle. Okay. This is the so clearly, as far if I am focusing on the particle, okay, the temperature of this particle is going to be a function of x, y, z and t, right. Temperature, this particle is moving around, temperature is going to be a function of spatial coordinates and time, and because I am following the particle, x is and y and z are also going to be functions of time. At a particular time, this is my x, y, z. At some other time, my x, y, z is different, some other time x, y, z is different. So, basically what I am trying to tell you is that these are all functions of time. The coordinate, I am focusing on a particular particle now, on a particular molecule, okay. I am not fixing my position. So, the temperature is a function of all the independent variables, that is what I have written, x, y, z and t, and I am saying that x, y, z and are functions of time, because the particle is moving, okay. So, now I am interested in how does the temperature of the particle change with respect to time, okay. So, that is the question. So, how does the temperature of the particle change with respect to time? So, what I am interested in is the particle is moving, I am interested in dt by dt, and x, y, z are functions of time, and there is an explicit dependency on time as well, okay. So, basically I am going to write this as dt by dx times dx by dt plus dt by dy by dt by dt plus dt by dt. So, when you are doing partial derivative, remember all the other variables are constant, okay. So, that is basically what I have done. I have just used something like chain rule or whatever it is you want to call it, formula for differentiation, which you are comfortable with from mathematics, okay. And dx by dt, dy by dt, dz by dt are what? How does the position of the particle change with respect to time? So, dx by dt tells you the x component of velocity, dy by dt tells you the y component of velocity, okay. So, dx by dt is ux. Similarly, dy by dt and dz by dt, okay. dy by dt is uy, that is the x y component of velocity. Okay. So, because the particle is moving, it has a velocity, and dx by dt is x component, dy by dt is y component. Now, what is temperature is a scalar function, so gradient of T is written as I dt by dx plus j dt by dy plus k dt by dz. I, j, k are the unit vectors. Okay, this is how the gradient is defined. What is the gradient of temperature? Okay, temperature is a scalar, gradient is a vector, and I, j, k are the unit vectors in the x, y and z direction. Similarly, u is I times ux plus j times uy plus k times uz. That is your velocity of the particle, the velocity vector. Velocity is also a vector. So, what I can do is, I can write these three terms as u vector dotted with gradient of t. Okay. So, I can write this as dt by dt is u dotted with gradient of t plus partial derivative of t with respect to t. Okay. I mean u dot del t are these three terms. So, u dot del t are the is equal to dt by dx, dx by dt plus dt by dy times dy by dt plus dt by dz times dz by dt. Okay. So, the point is that dt by dt is the is time derivative of a particle and partial derivative with respect to time. Remember, again, partial derivative is when all the spatial coordinates are fixed. Okay, this is at a fixed point. So, this is what we call Eulerian and this is what we call Lagrangian. So, that is the relationship between the Lagrangian derivative and the Eulerian derivative. Okay. When we are focusing our attention at a fixed point, that is the partial derivative. So, this is the, if you keep a temperature probe at a fixed point and measure what the changes are at that point, you will get the partial derivative. What you are calculating is partial derivative of t with respect to t. If your probe happens to be moving around with the fluid, okay, and you are recording the temperature, then you are calculating the left hand side. Okay. So, this is when the probe is moving around with the fluid and you have to imagine some situation where you can do that, and this is when the probe is fixed. So, in some sense, I mean mathematics, you must have gotten the concept of partial differential and total differential. Okay. So, this is, I mean you would have definitely come across that, what is the total differential and the partial differential. So, and you must have studied this formula somewhere in your life, dt is equal to dt by dx plus dt by dy plus dt by dz plus dt by dt. Yeah, yeah. So that's basically what it is, right? So this is my, yeah, sorry, dt by dt. So this left hand side is my total derivative, okay. This is my total derivative and these are my partial derivatives. So basically, I mean, what was a mathematical concept earlier, I am trying to tell you physically it corresponds to this different change of reference, the two different reference frames that we have, okay, Eulerian and Lagrangian. At that time you may have just not understood the physical basis, okay. So I am just trying to tell you that is what it is, okay. Now when you talk about steady state, we mean that things do not change with respect to time, and you can see that there are two time derivatives. Which time derivative are we talking about? The time derivative we are talking about is the one which is the partial derivative. When I say steady state, I mean at a fixed point I am making a measurement and that is not changing with respect to time, okay. I am not talking about the total derivative, I am not talking about the left hand side, the Lagrangian derivative, I am talking about the Eulerian derivative. So this is the Eulerian derivative, this is the Lagrangian derivative, okay. When I say steady state, I mean this Eulerian derivative goes to 0. So this is what we started out to do, this is Eulerian, okay, and this is Lagrangian. So at steady state, the Eulerian derivative is 0. So at steady state, the Eulerian derivative is 0. That means or no change with respect to time at a fixed point. So now what I want to do is just to give a simple example to help you understand things better. This is a converging channel, okay, the cross section is changing and there is a liquid which is flowing. And we keep our life simple and we say that this is the x direction, this is the y direction. To keep life simple, we will just say the velocity, there is only one component of velocity which is Vx and it does not vary in the y direction, okay. Velocity is only in x direction and it is independent of y, just so that I can illustrate the idea. So consider Vx to be independent of y and z, okay. Now you know that because the cross section is decreasing, the velocity is going to increase because you have an incompressible liquid, okay. So the same volumetric flow, same mass flow has to go through at every point and therefore you have velocity will increase, okay. Velocity increases with what? X, okay. So and at every point in this channel the velocity, let us say, does not change with respect to time, okay. So we have what is called the steady state situation. So if you have the steady state situation, consider steady state. That means dVx by dt is equal to 0. Okay. I wrote the earlier relationship between the Lagrangian and the Eulerian for temperature. I am going to now write the same thing for velocity in the x direction. Okay. With any property, it does not matter, I just chose temperature. So now I am saying we have similarly dVx by dt equals V dotted gradient of Vx plus dVx by dt. What have I done? Replaced temperature with Vx. Earlier argued temperature is changing, I am talking about Vx now. Vx is my property that I am looking at. Okay. So now, because of the steady state assumption, this guy goes to 0. Okay. And what is this going to be? Vx I plus Vyj plus Vzk, that is your velocity vector, and the gradient of Vx is I dVx by dx plus j dVx by dy plus k dVx by dz. This is the definition of gradient. Okay. And what I am assumed is that this velocity does not change with x, no, does not change with y, does not change with z, only this remains. When I do the dot product, there is a dot here, okay. Do the dot product, I get Vx dVx by dx. I just put total derivative because Vx does not depend on anything else. So now the particle is accelerating, dVx by dt is accelerating. Okay. This is not 0 because the molecules in the pipe, they are at low velocity. As it goes to the constriction, the velocity increases. So as far as the molecule is concerned, the velocity has increased, but at each point if you were to make a measurement, the velocity will be constant. Okay. So here is an example of this is not equal to 0, velocity of the molecule increases with time, or molecule is accelerating. Okay. So the particle is accelerating and it is occupying different positions at different times. So this is basically to try to explain to you what the difference is between the Eulerian derivative and the Lagrangian derivative. What I have done is I have basically spoken about a fixed point in space and a fixed molecule. Fixed point in space is infinitesimal. Okay. What we want to do is extend the same thing to a microscopic region. Okay. And how do we extend whatever this idea is, because whether you are talking about Lagrangian or Eulerian approach, this relationship between the Eulerian approach and the Lagrangian approach, we want to extend it to a larger region in terms of control volume and control mass, because tomorrow I may be doing a mass balance or an energy balance around a control volume. Okay. So this particular extension, this is what is called Reynolds transport theorem. So this relationship between Lagrangian and Eulerian, when I extend it to a finite volume, finite mass, not infinitesimal, not a particular volume, not a particular point, this is called Reynolds transport theorem, and that is what we are going to do next. Okay. The extension of this relationship between the two approaches for a finite volume or finite mass is okay. So, now I want to just introduce a few things. What is the meaning of control volume? Control volume is a fixed region in space, okay. The fixed region in space, that is my control volume, and this is something like a fixed point in space that we spoke about in the Eulerian approach, okay. And okay, the control surface is the boundary of the control volume. CV is control volume, okay. The other thing I want to talk about is control mass. This is a fixed mass of material or molecules. So, this is my, I am focusing my attention on my fixed mass, then that happens to be the Lagrangian approach, okay. Earlier I was talking about one molecule, one particle, but now I have a whole bunch of molecules. I am just focusing on that. That guy may move somewhere, but whatever it is, every time I am focusing on the same collection of molecules. So, that is my control mass. So, control mass is like a closed system, okay. Control mass is like a closed system because the mass is remaining constant, it does not change, whereas control volume is a fixed thing, something can come in, something can go out, okay. Different molecules can come, different molecules can go, they may or may not be equal. So, that is my control volume, and like I said, control volume is similar to the Eulerian thing where you are focusing at a fixed point, and control mass is the Lagrangian thing, okay. So, now what we need to do is take this do this extension. When you are doing all these conservation laws, we are going to focus on extensive properties, properties which are dependent on the mass, okay. So, conservation laws are applied to extensive properties. So, for example, mass, momentum, momentum is what? Mass into velocity. So, if the mass is more, momentum will be more. So, it depends upon mass, that is what I mean by extensive, okay. And so, what I want to do is talk about how to go from extensive to intensive. The so, for momentum, the corresponding intensive property. Intensive property means it is independent of mass. It is momentum per unit mass. Supposing I am talking about what is the momentum per unit mass, so mass gets scaled out, okay. So then what will am I remaining with? Velocity. So this is momentum per unit mass, which is momentum divided by mass, and that is velocity, okay. So the corresponding intensive property for momentum is velocity, that is independent of mass, okay. So now let us sit down and see what we have. I need to plan this thing properly so I don't make a mess. So I have this nice oval, okay, and this is my control volume. What is inside is my control volume. So this is what I said, a fixed finite region in space, okay, it is occupying some volume, that is my control volume. The boundary surrounding it is my control surface, okay. Now at a particular time t, the mass inside the control volume is identified as my control mass, okay. So at time t, the control volume could be this room, control mass is everybody, me, you, all the molecules sitting here, that is my control mass, okay. Now at time t, the control mass is occupying control volume. Because of the flow, what is going to happen? Some of these let us say the flow is like this, that is my flow direction. The molecules inside are going to move out, right. So the molecules now are going to occupy the dashed region, okay, the portion occupied by the dashed. Why is it dashed? Because there is flow in your system. We are talking about flow problems, right. So there is fluid flow. So whatever was inside at the time t plus t has moved out, and at t plus delta t it is going to occupy this dashed region, okay. So at t plus delta t, the control mass occupies the dashed region. Now the same molecules I am talking about, okay. Control volume remains the solid thing. At time t, control mass is occupying control volume, at t plus delta t, control mass is moved out. So now I am going to divide this thing into 3 regions, okay. I am going to call this region 1, region 2, and this region 3. Is this clear? Region 1 is the one where the molecules are present at time t, the portion of the control volume occupied by control mass at time t, a part of it. Region 2 is also is common to the molecules in the control mass at time t and t plus delta t. Region 3 is the molecules which have left the control volume, okay, and now at time t plus delta t they are outside. So I have basically divided my control mass into 3 portions, okay, and that is what I have done. let us start with region 3. Three has molecules from the control mass which have left the control volume at T plus delta T. Okay. Region 2 has molecules which are in the control volume at T and T plus delta T. And region 1 has molecules which were occupied by the control mass at T, only at T. Okay. I mean at T control mass occupies 1 and 2, at T plus delta T it occupies 2 and 3, that is the point. Okay. So, at T control mass occupies 1 and 2, at T plus delta T control mass occupies 2 and 3. This may be more clear. Okay. Later time instance the control mass is occupying a different region. So, because it is moving, the region of space is occupying is different. So, 1, 2 and 3 are spatial regions, okay. But the molecules are the same in 1 and 2 at T and 2 and 3 at T plus delta T. Okay. The molecules at time T in regions 1 and 2 are the same as the molecules at time T plus delta T in regions 2 and 3. Okay. So, now what I want to do is same thing I want to relate. So, how do I extend what I did earlier? I want to relate the changes in the control mass to the changes in the control volume. Okay. Control mass is fixed molecules, control volume is fixed space. So, Lagrangian, Eulerian, okay. That is the thing we want to do. So, now I am going to call this ddt of NCM, that is, this is my property, N is my property, it could be momentum, it could be whatever, okay. N is my property, Cm is my subscript for control mass, and what is the rate at which this property is changing, okay. This is limit of delta T tending to 0, and what is the property? I am putting in triple integral because it is over the control volume, okay, but not triple integral over, let me do this in 2 steps. This is NCM at T plus delta T minus NCM at T divided by delta T. This is the classical definition of derivative. What is the property in the control mass at time T plus delta T minus what is it at T and divided by delta T, take the limit as delta T tends to 0, okay. This is just the definition of derivative, and what I am going to do is I am going to relate this to volumes. So, this is going to be evaluated in regions 2 and 3. This is going to be evaluated in regions 1 and 2, okay. So, I am going to write the right hand side as integral regions 2 plus 3, okay, of eta rho dV, okay, minus integral in regions 1 and 2 of eta rho dV. Okay, I will just tell you what is eta. Eta is the corresponding intensive property, N is the extensive property, rho dV, rho is density. Okay, so remember N is like eta rho dV or dN. So you take a small volume element, okay, you take a small volume element dV, you multiply it by rho, you get mass element, multiplied by eta, you get the property. Okay, eta is the intensive property, like I said, for momentum, eta will be V. N is momentum. Okay, so what is the momentum in a particular volume? In a particular small dV, it is what is the velocity in that, eta is velocity multiplied by the mass in that, rho dV is the mass. Okay, that is what I have done. I have just shifted from this thing, and then I need to put some divide by delta t, no? I forgot the divide by delta t and look at the limit of delta t tending to 0. Okay, we will continue this thing in the next class, and that will basically tell you what is this Reynolds transport theorem. Thank you.